When we talk about AI memory, what comes to mind? Probably something like a hard drive, right? Just a place to dump information. But what if memory could do way more than that? What if it could actually understand the connections between all the things it remembers? Well, that's what we're diving into today. A new kind of AI that doesn't just store facts, it reasons about them. Okay, so the key idea here, the big concept, is something called relational reasoning. Let me give you an example. Imagine you're in a park and you want to sort all the trees by how far they are from one specific bench. It's not enough to just know where each tree is and where the bench is. You have to calculate and compare the relationship between them, the distances. That is relational reasoning, and it's something we humans do without even thinking. But here's the thing. For AI, this has been a surprisingly tough nut to crack. I mean, these models are incredible at memorizing just insane amounts of data, but they often really struggle to explicitly reason about the connections inside that data. And to get why, let's take a look at some of the standard models, like LSTMs. Think of them like a super long, continuous scroll of notes. They're awesome for keeping everything in order, in a sequence. But what if you need to connect a note from the very beginning with one from the very end? It's almost impossible. The model just doesn't have a built-in way to let those two distant pieces of information talk to each other directly. So this all leads to a really fundamental question, right? Can we design a memory that isn't just a passive filing cabinet, but more like an active workspace, a place where ideas can be compared and contrasted and actually connected? Well, that's exactly what the researchers at DeepMind decided to tackle. They built a brand new memory module designed specifically for this, for relational reasoning. And here it is, the Relational Memory Core, or RMC for short. The whole design philosophy behind it is simple, but it's incredibly powerful. Just give memories a way to talk to each other. So instead of being these isolated facts on a long scroll, they become active players in a network. Okay, so how does this actually work? I mean, how do you get bits of data stored in a memory matrix to start interacting and reasoning with each other? Well, the answer lies in a mechanism that's pretty much at the heart of modern AI. So the engine driving this whole thing is a process called multi-head dot product attention, or let's just call it self-attention, and it is an absolute game changer. Why? Because it lets every single memory in the system look at, compare itself to, and pull info from every other memory all at the exact same time. Yeah, it sounds complicated, but we can really break it down into 3 simple steps. First, every memory slot creates a query. It's basically asking, hey, what information am I looking for? Then it compares that query to the keys. Think of them as labels of all the other memories to see which ones are the best match. And finally, it pulls in the values, which is the actual information, from the most relevant memories to update itself. Now, the really amazing part is that this isn't some slow one-by-one check. It's a massive parallel conversation where every single memory is updating itself based on what all the other memories know all at once. It creates this dynamic, constantly evolving web of relationships. All right, so the theory sounds fantastic, but does it actually work in practice? To find out, the researchers just threw a series of incredibly difficult challenges at the RMC, tasks that were literally designed to break standard AI models. And they didn't just use one test, they used a whole bunch of them, from reinforcement learning games like mini PacMan to evaluating computer code and even really complex language modeling. They wanted to see if this new reasoning ability would actually hold up across totally different fields. But before all that, they came up with this brilliant little task that was a pure direct test of relational reasoning. The model sees a sequence of vectors. You can just think of them as points in space. And then it gets asked, what is the nth farthest vector from this other specific vector? Now, to solve this, you can't just remember where the points are. You have to compute the distances between them, sort those distances, and then find the right one. And the result? The Relational Memory Core absolutely crushed it with a stunning 91% accuracy. This was a huge, huge win. But look, that 91% number is only half the story. What makes it so impressive is when you compare it to the others. As you can see here, standard models like LSTMs and even more advanced memory networks, they just completely fell apart. They scored less than 30%. They simply weren't built for this kind of relational task, which proves the RMC had a fundamentally new skill. And this is where it gets really cool, because we can actually peek inside the model's thought process. This visualization shows us the attention patterns between memories. At first, before the model knows which vector is the important one, its attention is all over the place. It's just kind of taking everything in. But then, watch what happens. The moment the reference vector is identified, that's the one marked here in red, the entire system just snaps into focus. All the other memories immediately direct their attention to the memory holding that key piece of information. This isn't just passive storage, people. This is active directed reasoning happening in real time. We're literally seeing the model figure out which relationships matter. And this success wasn't just a fluke on that one task. They tried it on something really complex, understanding and executing computer code. And again, the RMC blew the other models out of the water, especially on the full, tricky programs. It was just plain better at understanding the symbolic relationships between things like variables and operations. Moving over to the world of reinforcement learning, the results were just as dramatic. In a game of mini PacMan, the RMC agent scored nearly double what a standard LSTM agent could manage. Why? Because its ability to reason about the relationships between the ghosts, the food, and the maze itself led to much, much smarter gameplay. And finally, even in the super competitive world of language modeling, the RMC set new state-of-the-art results across 3 gigantic datasets. This really shows that being able to reason about the complex grammar and meaning between words gives it a serious advantage in understanding human language. Okay, so let's zoom out. What's the big picture here? What does all of this really mean for the future of AI? The really crucial takeaway is this. Instead of just training these huge AI models and hoping they figure out how to reason, we can actually build that capability right into their architecture. By designing a memory that is meant to interact and form connections, we unlock the ability to solve a whole new class of problems that were just impossible before. It's a fundamental shift in thinking, from passive storage to active reasoning. And that leaves us with a pretty fascinating thought to end on. For all of human history, our progress has been driven by our ability to connect different ideas to create something new. Now, if we can give AI that same fundamental ability, not just to know a bunch of facts, but to truly understand how they all relate to each other, what kind of amazing new solutions and what unforeseen discoveries might it help us find next?